Temperature dependence of saturation magnetization. Magnetization is magnetic moments per unit volume. In ferromagnets, there is a finite magnetization, that is, magnetic moments are aligned in a particular direction. But if temperature is increased, it will randomize and magnetization will decrease. Therefore, magnetization depends on temperature. To find the dependence, let us use mean field approximation, that is given by this equation: magnetization equal to lambda into field B. Lambda is a constant called mean field constant. Below Curie temperature, we will find the relation between magnetization and temperature. Above Curie temperature, ferromagnetism disappears and the specimen behaves as paramagnet. Let us use Brillouin expression we found out for the magnetization of a system having spin magnetic moment only. There is no orbital angular momentum or orbital L equal to 0. In this case, magnetization we have determined and it is equal to, in paramagnetic case, we have determined magnetization equal to n mu tan h mu b by kt. This was the expression we have found for paramagnetic magnetization. Now, let us introduce two quantities. First one is called reduced magnetization. It is defined as m equal to small m equal to capital M by n into mu. The capital M is magnetization and n is the number of ions or concentration in the specimen. Mu is the magnetic moment or spin magnetic moment. And another quantity we introduce is reduced temperature. It is equal to temperature T into Kb by n mu square lambda. These all are constants. Now we can use the expression, the above equation of magnetization, that is m equal to n mu tan h mu b by kt, and taking n mu to left hand side we get m by n mu, which is reduced magnetization, and the term inside the bracket we can replace by m by t. It is shown here how the term inside the bracket becomes m by t. Thus, this is the new relation between reduced magnetization and reduced temperature. Now, let us plot left hand side and right hand side as function of m at different values of reduced temperature T. This is the figure. Here, x-axis shows reduced magnetization and we are plotting left hand side and right hand side functions. That is, left hand side is reduced magnetization. When we plot m with respect to x-axis, we get a straight line. And we are plotting right hand side, that is tan h m by t for different values of t. T equal to 0.5, t equal to 1, t equal to 2. And for t equal to 1, we can find that the left hand side and right hand side is equal for most of the values of m. But then it deviates at higher values of m, reduced magnetization. And for higher temperature, than T equal to 1 reduced temperature, the magnetization is 0. And for lower value of reduced temperature than T equal to 1, it will satisfy only at a single point. Therefore, T equal to 1 can be considered as the point, a critical point, and we can find out from this equation critical temperature Tc equal to n mu square lambda by Kb. And when T increases above 1, m reduces to 0, which is ferromagnetic behavior. That is, when temperature is greater than the Curie temperature, it becomes paramagnetic and magnetization disappears. But this theory, mean field theory, cannot hold good description for a variation of M at low temperatures, that is below critical temperature. Below critical temperature, this tan function, tan of h of m by t, becomes very large, and we can equate it by this equation. It can be approximately equated as 1 minus 2 epsilon 2 exponential minus 2 by epsilon, and therefore let m of 0 be the maximum magnetization possible, that is at 0 Kelvin, and m of t be the magnetization at temperature T. The difference between magnetization, that is with increasing temperature, magnetization deviates by an amount delta m that we can approximate as this difference from 1, that is 2 exponential minus 2m by t. That is given by this equation number 3. Variation with temperature, magnetization deviation with respect to temperature. Now, saturation magnetization of a specimen at absolute zero is given by this equation. Ms of 0 is equal to Nb capital N mu b, where N is the concentration, mu b is Bohr magneton, and Nb is the effective magneton number.